Hi everyone and welcome. Today's presentation is going to take you through a validation study of FDS on the area of external fire spread. My name is Markus Nilsson and I work as a fire safety consultant at Brandskyddslaget in Stockholm. The other co-authors of this report is Johan Nilsson and Axel Mossberg. So it's a pleasure being here today presenting the results of this paper called Validating FDS against a large-scale fire test for facade systems. And the background to this work lies partly in the results of my master's thesis conducted at Lund University called The Impact of Horizontal Projections on External Fire Spread. And I was reflecting on yesterday's talk from Kevin McGradan when he talked about new students validating stuff. And I came up with two conclusions, two major mistakes from my side. Two of two. The first one, I chose the sexy side of fire modeling. I chose FDS instead of CFAST. And the second one was that I didn't initiate the contact with NIST prior to the studies. But hopefully the results will come up still and not fall in between the tables. So in today's lecture, I'm going to start with an introduction which talks more about the background to this work. Then I move on talking about the experimental setup in FDS and from the actual test. I then move on showing you how some of the data were processed to compare to the data in FDS. And then I'll give you a few examples of the results and also some comparisons to the former version of FDS. And then I end with some concluding remarks. So, in the thesis, the main goal was to see what type of effects different protective measures had on the external fire spread. And to investigate this, a calculation tool was needed. And to be able to model the external fire spread. And after some research, FDS was pointed out as a good contender for that one. However, to get an understanding of how FDS performs in these types of geometries, and in order to know that credible results were obtained in the following comparative analysis in the thesis, the tool had to be evaluated. And a couple of years ago, Swedish Technical Research Institute of Sweden did some large-scale fire testing on a slightly modified SB Fire 105 test rig. And SB then also did some numerical work on that specific test on FDS version 553. But at the time I did my thesis, FDS version 620 was the latest update. And an update doesn't automatically mean that every area is improved. So I thought that possible changes were important to address. And these factors were the driving forces for why I, as a student, took on a validation study on FDS 620 on that particular fire test. Let's take a look at the experimental setup. So the SB Fire 105 test rig in itself simulates a fire on ground floor of a 3-story building, and from that it's measuring the impact on the facade systems fitted on the test rig above. And in a series of tests for evaluating fire growth of external combustible ship surfaces, non-combustible pneumatic sheets were attached to the facade. And this is that specific test you see this drawing on the screen here. So the test rig is around 7 meters high. The fire compartment below is around 3 meters wide, the opening, and 0.7 meters high. And the facade is 4 meters wide and 6 meters high. And temperatures were retrieved at 6 positions along the height of the facade, as you see here. And that was retrieved by thermometers, plate thermometers, and by thermocouples. And you see the plate thermometers here is like black squares going from position C21 in the bottom up to C26 in the top. And then you see the thermocouples next to it, I think it was 50 millimeter offset and from the surface, from position C27 up to C32. And the first measurement position here is starting at approximately 0.5 meters from the opening. And then there was a measurement every 1.1 meter along the facade. So in the fire room, 2 trays were filled with 60 liters of heptane, which corresponded to a fire of around 3.1 megawatts, which was estimated by a large calorimeter that was fitted above the test rig. And here are some real pictures on the fire development. So to the far left, you see the test rig before the start. Looks pretty. And then it's the fire development after 240 seconds, 600 seconds, and 780 seconds. Just to give you a feel of the magnitude of the fire here. So quickly the setup in FDS. Here you see a quick setup. So the far left picture, you see the FDS setup from front. And to the right pictures, you see the close-up on the measurement devices. And measurements of the convective heat flux, the incident heat flux, and the adiabatic surface temperature took place at each height. And the temperatures retrieved from the plate thermometers were actually modeled in FDS. So a plate thermometer, it's basically built up by a steel plate with a thermocouple welded on its backside. And behind that, you have insulation fiber boards. And this was emulated in FDS by applying surfaces with steel and insulation materials and their thermal properties. And then behind that, we fitted a wall temperature meter that measured that exposed surface in FDS, the temperature of that one. That was how it was emulated in FDS. I'm going to talk more about the use of plate thermometers and adiabatic surface temperatures in a minute. But first, let's take a look on a very crucial part of the validation study, how the data was processed. So to start with, I'm going to show you how some of the temperature data was used to calculate the incident radiation during the test. So you see equation 1 in this box we used to calculate the incident radiation during the test, and then equation 2 here, the convective heat transfer, HC, it was calculating using this one here. And these equations are found in the test report from the combustible ship surfaces report I talked about earlier. So this is where the plate thermometer comes in. So equation 1 up here, in turn, is based on a simplified heat balance equation of a plate thermometer, as described by Ulf Wikström. And we see that one later down here. So the far left term on that one describes the radiant heat that is absorbed by the plate. The second term is the heat that is emitted. The third term here is the heat lost by convection. And then the fourth one is the conduction, the heat loss through conduction through the insulation pad and along the surface. And the term here on the other side is a simplified way, the rate of heat stored calculated by lumped heat capacity. So by neglecting the conductivity loss here and by moving around the terms, equation 1 up here was formed. So the plate thermometer measures approximately the temperature of a surface which cannot absorb any heat. So this temperature is also called the adiabatic surface temperature. And it's an illustrative temperature measure, both taking into account the radiation and convective heating from the surrounding gas. So very simple ways is that saying that if an exposed body is far away from the fire source, it will be mainly exposed by radiation, and hence the adiabatic surface temperature will be closer to an effective radiation temperature, the TR. But if the exposed body is exposed by mainly convection, the adiabatic surface temperature will be closer to the gas temperature. So it will move around as a sort of an average. So the temperature TPT here is the retrieved temperature from the plate thermometer, which is an approximation of an adiabatic surface temperature. So the good thing with this measure is it can be used as an alternative means of expressing a thermal exposure to a surface without taking into account any loss through the gain through the exposed body. You can also use it later to separate heat transfer programs and stuff. And I guess you're wondering about equation 3 here. There it is. And that was just a way for me to say that because this is the incident radiation, not taking into account the convective heat flux here, I call it the incident radiative heat flux to kind of follow the same heat flux terminology as used in FDS. So this was needed in order to compute, to be able to compare the heat fluxes in FDS. And this is how I'm going to show you how I did that now. So from Christopher Overholt's website, I found the following expressions, which I thought clarified the mathematical reconstructions of the different heat fluxes a bit compared to the FDS user guide. And so in FDS, there is a quantity called incident heat flux up here. which is the sum of the incoming radiation and convection, including outgoing radiation. And there is also a quantity called the radiative heat flux down here, which is given by the sum of the incoming and outgoing radiation. So by substituting equation 5 into 4 enables one to see the incident radiation as in equation 7 here. And the last step to really be able to compare these heat flux to the ones that were used in the experiment, I had to subtract with the convective heat fluxes. That was how I did in FDS to compare to the actual test. So, in other words, the incident radiation, incident radiative heat flux in FDS that were compared with the ones from the actual test, they were done by placing a device measuring the incident heat flux and subtract with the convective heat flux on that position. That was how I compared it. So let's take a look at the results. So since there are a lot of results in this paper, I chose to focus only on the grid sensitivity study here today. And this is also because it's shown to have the greatest effect on the end results. And these simulations were performed on a single mesh, and mesh resolutions, the cell sizes were 20 centimeter, 10 centimeter, and 5 centimeter. And that would correspond to a mesh resolution D star delta X of 8, 15, and 30 for the coarse, medium, and fine grid. So we start by looking at the retrieved temperatures from the thermocouples. So in the left graph, the results from the 3 closest positions to the fire are seen, and to the right we see the 3 positions further up along the facade. So the temperatures from the actual test are seen as normal lines, and the temperatures from FDS are seen as dotted lines. So as seen in the figure, the overall distance between the coarse cell size and the finer cell size is pretty considerable. So we see that the 20 centimeter consequently underestimate the temperature on all heights. By looking at the data from the 10 centimeter cells, you see that it's pretty comparable at the 3 closest positions, the 3 positions further up along the facade, but at the 3 closest positions to the facade, it has a little bit problem to meet the target. The 5 centimeter grid, on the other hand, seemed to slightly overestimate temperatures further up along the facade, but close to the facade, it's, in this case, pretty spot on. So, moving on to the thermometers. So, similar tendencies are seen in the result for the thermometers. So, in these figures, the same type of setup, but we're looking at the thermometer temperatures and the modeled thermometer temperatures in FDS. We see that the 20 centimeter cells have really hard time to meet the actual temperatures, and the finer grid size have mostly problems to meet the temperatures further up, close to the fire here, the first position. So in this graph, we're looking at the temperatures retrieved from the plate thermometers and the modeled adiabatic surface temperatures in FDS. So compare with the previous graph, I don't know if you've seen it, but the values have increased a bit. And generally for the 5 centimeter grid, the AST, the adiabatic surface temperature in FDS, are higher at each position along the facade. But at one position, and that makes sense, because it's reasonable, bearing in mind that what I talked about before, that the temperatures retrieved from thermometers are only approximation of the adiabatic surface temperature. So the thermal inertia of the steel plate and the heat loss through the insulation padding, those are factors that means that the thermometer temperatures become lower than the adiabatic surface temperature. But at the position closest to the fire here, you see that the FDS temperatures, the adiabatic surface temperatures, are lower than the model plate thermometers. And that's a contradiction to what I just said. I don't know also if you have noticed, but this shape of this first measurement line here is different compared to the other ones. So the reason for the strange shape of the first measurement position could be due to the facade cladding, which also may explain the lower temperatures. So In the thesis, an uncertainty analysis was performed, which showed that the uncertainty in the computation of the heat fluxes lied in the measurement of the thermometers. And after observing the footage in the fire scenario, it was seen that the Prometec cladding were hanging loose partly in the bottom of the facade, which is a big of damage. And this may have caused changes around the flow field, which then affecting the measurements and then the calculations. This could be the reason for why it looks like that. Moving on, so this graph shows the calculated incident radiative heat flux result from the experimental data and the ones that was produced in FDS. So as seen here, the 5 centimeter grid slightly overestimates the heat fluxes on all positions, except on the first position here, which still has some problems to reach the actual computed heat flux. And again, the coarser cell sizes have problems on each height to reach the actual heat fluxes, other than on the positions higher on the facade. So, since numerical work has been conducted on this test before by SP, a comparison between their work on FDS version 553 to my work on FDS version 620 was made. So, to the left, we're looking at the temperatures retrieved from the thermocouples again, and to the right, the thermometers. And this time is only on the 3 position closest to the fire. And we can see that smaller discrepancies are found between the program versions regarding the thermocouples. Larger discrepancies are found regarding plate thermometer temperatures, where FDS 620 are seen to produce slightly higher temperatures than FDS version 553. And larger values are also produced in FDS 620 regarding the incident radiative heat flux values. And one of the biggest changes between the program version is the implementation of a new model for turbulent viscosity. So in FDS version 553, the Smagorinsky model was used to model the turbulence, while in FDS 620, the Derdorf model is used. And this model determines to a large extent the dynamics of the fire. And a thesis from Stord Haugesund University in Norway performed numerical work on a large-scale fire test similar to this one. The main goal in that study was, however, to look at an ejecting plume and the thermal impact on steel structures outside. And they discovered that in FDS 553 was not able to simulate the gas temperatures out from the opening. So the ejecting fire plume was ejected further away from the facade compared to the actual test, compared to the data and pictures. And after they used the beta version of FDS 6, they saw that the plume all of a sudden ejected closer to the facade, corresponded better with the measurements, and the actual photos look better. So, given this, the main reason for the higher output data for FDS 620 compared to FDS 553 here may be due to the change of model for turbulent viscosity. So that affected maybe the velocity field through the opening, hence also the appearance of ejecting plume, and then the impact on the facade. So over to some conclusions. As seen in the main results I presented to you today, FDS 620 generally produce higher temperatures and incident radiative heat flux results compared to its predecessor. From the results, it's also shown that FDS 620 produce results that are more in line with the test data than the former version. And from my point of view, I think FDS version 620 reproduce the actual data with a reasonable level of detail. However, note that in order to achieve this, primarily a very high measure resolution was needed, namely a D star delta X of 30, which is 5 centimeter for this 3.1 megawatt fire. And finally, I claim that from an ordinary FDS user perspective, the use of heat flux in FDS is a bit confusing. So there are plenty of choices for the user, but unless you're not familiar with or develop the FDS codes, it's hard to know what type of heat flux you will get out from a calculation. For example, regarding the term incident heat flux, when I read that term, I refer to a flux that is coming into a surface, not yet penetrating the surface. And the incident heat flux should then only include the gross heat flux terms. But in the incident heat flux definition, you have the convective heat flux. And the convective heat flux term involves the net heat flux, the net flux. And at least from the information I was provided from Overholt. And this is where it all gets confusing in FDS, when the net heat flux is involved in a gross heat flux terminology, which I think could mislead the ordinary FDS user that is not into the code and digging down deep. So, and yeah, no, usually the convective part of the total heat transfer is small, and in many cases potential errors would not be notable, but it could be a problem in certain situations. So instead of using heat fluxes, kind of promoting Ulf Wikström here, things, I'm saying that using another way of specifying this thermal exposure to a surface, you can use the adiabatic surface temperature, especially if you have a comparative analysis where you don't want the absolute assessment, you want to compare the total damage on a surface, then the adiabatic surface temperature is really good. And what you saw on the results here is it has great potentials. And later, when you have the adiabatic surface temperature, if you want to, you can calculate the incident radiative heat flux results with the equations I showed you earlier. That's another way of doing it. So with that, I just want to say thank you for listening.
Okay, you stopped almost exactly on time. You were 1 minute early, so thank you. Okay, so any questions, please? Yeah, Kevin?
So you've had long discussions with Ulf Wikström too?
I'm not from the same university, but I have had discussions with him.
I can't tell you how many hours I've debated heat flux.
He has said the same.
Yeah, I know what you mean. Heat flux is a very confusing topic. That's why when I've simulated some of the experiments that Ulf and his students have conducted, I just literally compare the plate temperature directly.
Yep.
So within FDS, you can model, the heat transfer through the thin plate of Inconel and then the insulator. So that's the least confusing thing, because otherwise, how FDS converts to the adiabatic surface temperature and how you would do it from the plate, and then of course looking at thermocouples, that's a whole other ball of wax. So I tend to just focus on the plate temperature directly. As for the results, Charlie asked the question the other day about transients and why we always go for the steady state. This is a perfect example of why, because you can see that it's difficult to compare model and experiment when the heat release rate is changing in a sort of non-predictable way. I mean, he's burning a pan of liquid. What I would suggest in a test like this, and what we have done at NIST over the years, is instead of using a pool of liquid fuel, we spray the liquid fuel out of a nozzle into the pan, and that way we can control very carefully the fuel flow rate to the tests. So what we tend to get then is a much more uniform heat release rate, because in a test like this, what's really important to compare the model with the experiment is when you have that, relatively long, constant time period where things aren't changing.
Yeah.
And then it's a lot more clear, because when you're actually trying to follow a time-dependent heat release rate curve, it just makes the comparison a little more difficult. So if you do tests like this in the future, what I would suggest is to use a nozzle spraying down into the pan, and then you can very carefully control the heat release rate.
So in this case, I talked to SB about this, and they have problem just what you said, that the heptane fire just after a while just increasing a lot.
Yes.
Due to a some kind of boiling in the heptane.
Yes.
And the
Yes.
thing they did is to, actually in this case too, was to install a flame spreading lattice to kind of put down the pressure of the combustion. And they said that during these tests, because this was 5 years ago, they still had problems with that. But now when they're doing testing, they tend to see more of this one, and you have it straight and then down.
Okay.
So
Okay.
they're working with flame spreading lattices. They said something about that the whole test rig was not in level. So because of that, the water, because there was water and then heptane on top,
Yeah.
they tilted a little bit, and
Yeah.
that did something with the boiling and messed it up. And now they're more correct levered, the whole test rig, and with the flame spreading lattice and all that, the heat release rate curves seem to be very more stable.
Right,
Yeah.
right. Yeah. Good, thanks.
Yeah.
Any other questions? Okay. Well, thank you very much.
Thanks.
Very good.